That's totally fine. My pup, she is actually at boot camp. So we actually go pick her up today. So that'll be fun. So you might see her running around here a little bit in the quarter. Yeah. So today's lecture, we're going to finish up immuno, and then we're going to have kind of like a little admin thing in the middle where we're going to do that exam briefing I mentioned yesterday, and then we're going to get into a little bit of neurophys. Okay. Yeah. Questions from yesterday's material? I know it's a lot. Doing okay? All right. So, and then same thing, however you guys want to respond to me, you can unmute yourself and ask a question, or you can turn into the chat. I have the chat in the corner of my screen here. So if you guys have a question or you want to answer one of my questions, you can throw into the chat or say it. Either one's totally fine. Okay. All right, let's do this. So remember how we talked all about the immune system, first, second, third line of defense, and all those crazy cells and all of those interactions? Today, we're going to break it. So today is all about how your immune system kind of overcompensates or overcorrects. Okay. So first up, we're going to be talking about immunodeficiencies. Simply put, immunodeficiencies is just some sort of failure of said immune system. Okay. Now, the way I kind of think of this, immunodeficiency and being immunocompromised and being immunosuppressed. Okay, so these three terms are kind of used pretty often. Being immunocompromised or immunosuppressed, that is a type of immunodeficiency. So just broadly speaking, immunodeficiency, your immune system is lacking. Why? Well, is it compromised, i.e. you got something else going on, which we'll talk about, or is it being suppressed, like if you're on steroids or some sort of immune system, if you're on some sort of immune system inhibitor, okay? You guys can use these terms interchangeably. I'm fine with that. I know what you're getting at, but technically immunodeficiency is just the big umbrella that encapsulates everything, okay? So there are two types of immunodeficiency. It can be primary. Now, whenever you see primary in the medical field, it usually means congenital. What does congenital mean?
Acquired at birth.
Yeah, I'm just gonna say born with because I'm lazy. Yeah, so primary immunodeficiency or congenital immunodeficiency, person's born with this. So you guys know like the stereotypical like bubble boy, that's the idea there. Or maybe they're born with some broken immune system. Second type is secondary. Now, a little bit of wording here. Anytime you see the term secondary in the medical field, anytime you see the term secondary, I want you to think due to, okay? This is going to come up a lot in lecture. The way I kind of abbreviate things, you can say secondary as second degree, which is also D over T. So you'll see that those abbreviations quite often. So secondary means due to. So secondary means due to something else, i.e. it's acquired, okay? Let's see. So you can see a fever secondary to infection. Okay, so you can see a fever due to an infection. That's how those words kind of work. You're going to see them quite often. So secondary always means kind of like due to. Okay, so secondary immunodeficiency is usually caused by another illness, which we'll talk about. And I want to highlight that your secondary immunodeficiencies are much more common than your primary immunodeficiencies. Okay, so if somebody's going to have a broken immune system, how are they most likely going to get it? If someone's going to have an immunodeficiency, how are they most likely going to get it?
By like some other kind of illness.
Yeah, by some other kind of illness. Exactly. Exactly. Very good. Okay. So these are all your causes for those immunodeficiencies. You don't need to memorize this. The only one we're going to be talking about today is going to be acquired immunodeficiency syndrome, or AIDS. Okay. So AIDS is caused by a virus, caused by the human immunodeficiency virus, or HIV. Now, the weird thing about this virus and why we're highlighting this virus specifically targets your T helper cells. Your T helper cells. Does anybody remember what's the other name for your T helper cells?
The CD4?
Yeah, you got it. You got it. CD4. Okay. So if somebody gets this virus goes after your T helper cells. They go after your CD4 cells. So as a nurse, what kind of objective data would you look for to see if someone was HIV positive or negative?
Low CD4 count.
Low CD4 count or depleted T helper cells. Exactly. So what's the big deal? It's a virus that goes after a single type of cell. What do T helper cells do?
They command the rest of the other T cells, right?
Mm-hmm. Exactly. So if we were to trace this out here, somebody gets an HIV infection. That's going to go after their CD4 cells or their T helper cells. So we see a decrease there. Now your CD4 cells coordinate the entire system. What happens when your coordinators are gone? What happens to the army when there's no longer a general?
They're out of control.
Not so much out of control. It's just, how can I put this? Anybody ever work retail or fast food?
Unfortunately.
What happens if the manager's not there? What
Nobody
do you do?
knows what to do.
Yeah, nobody knows what to do. Therefore, no one gets anything done. Okay, so that we see a lowered immune response. So this is the analogy that I kind of think of. You have a car, yes? Now the thing that coordinates your entire car is your key. You stick the key in the ignition, you turn it, the electrical system meets up with the mechanical system, and things run. If I take your car to a garage and I completely disassemble it, it's in pieces all over the floor. What happens when you turn the key? Nothing happens, right? So what I'm getting at here is your immune system, all of the parts are still there. You still have neutrophils, you still have macrophages, you still have B plasma cells, but nobody's talking to anybody. Therefore, no one's getting anything done. Does that kind of make sense? Okay, so if you have a patient with, again, HIV positive, what would you expect their neutrophil count to be? Elevated, lowered, or within range?
Maybe elevated.
All the pieces are there, but nobody's talking.
So it would be normal. They're just not doing what they're supposed to.
Exactly, exactly. So it'd still be within range. Even if they have an infection, like a fever, you'd still have normal neutrophils. What should we see with a fever? What should happen to white blood cell count?
Increase.
You should increase. Who told us to increase stuff? The T helper cells. So you guys can kind of see all the pieces are there, but nobody's talking to each other. Okay. You do not need to worry about stats. Those change, so no worries. In terms of epidemiology, you need to know that it is blood-borne, okay? Don't need to worry about the other 2 points there. So why is HIV so dangerous or difficult to treat even? So again, this virus specifically targets your CD4 cells, right? You don't need to take pictures on, or you don't need to take notes on this if you don't want to. This is just me kind of explaining it. So it targets your T helper cells. Just like any other virus, it injects its RNA, boom, it goes in. The crazy thing about HIV is it takes basically a copy. It makes a copy of your DNA and it synthesizes a very specific to you virus. It mutates so quickly. It mutates so quickly. That's why it's so hard to treat, because it has everyone's fingerprint with it. So, all right. So what's the difference between being HIV positive and being or having an AIDS diagnosis? Okay. So with HIV positive, you know that you have the virus. In order to be diagnosed as AIDS, your white blood cells, specifically your T helper cells, need to be below a certain amount. Okay, so somebody is HIV positive, they have so many T helper cells. As this virus progresses, grows, your T helper cells decrease in count. Once we are below 200 cells per milliliter, now we call it AIDS. Okay. So let's think about this. If somebody has AIDS, so you know it's been going on for a little while, they've had HIV for a little while. If somebody has AIDS and they get the common cold, can they fight it? No, because no T helper cells, no response. So what kind of immunity do we need to give them? How could we help save this person? What would we want to maybe inject?
Antibodies?
Yeah, if we inject antibodies, what kind of immunity is that?
Artificial active? No.
Artificial, not active.
Passive?
Passive, correct. So this is an example where someone who is immunocompromised, they don't have time to learn. You need to give them the answers. Okay. So why is this relevant to you guys? Accidental needle sticks. Okay. Has anyone ever had an accidental needle stick and had to fill in an incident report? Maybe, okay. If you get an accidental needle stick, oh, there is a bunch of paperwork to fill out. Okay, let me tell you, there is no test that can tell you immediately if you have this virus or not. You have to wait 3 months before you can get tested. You have to wait 3 months of not knowing if your life is going to change or not. Does that give anxiety to anybody? Okay. Be careful when you guys are out there. When you're running down the halls with your needles, just make sure they're capped. Okay. And only run with 2 pairs of scissors, not 1. All right. So now we're going to be talking about hypersensitivities. When it comes to hypersensitivities, here's your definition: altered immunologic response, blah, 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 blah. What the hell does that mean? So let me kind of give you an alternate definition. A hypersensitivity is defined as an excessive / inappropriate immune response damaging the host when exposed to a sensitizing antigen. So an excessive / inappropriate immune response resulting in damage to the host when you're exposed to a sensitizing antigen. Sound good? Clear as mud? Okay, that's what I was looking for. So what the hell am I talking about? With a hypersensitivity, this is when your immune system freaks out. This is when your immune system freaks out and hurts you. Okay. Your immune system is supposed to protect you, yes? But if it goes crazy, it might attack you. So we're going to get into all the different types here, but think about anaphylaxis. If somebody has anaphylaxis, right? It's an allergy. Is it beneficial for you to release so much histamine that your throat closes up and you can't breathe? That is a hypersensitivity. You guys see how that is very excessive / inappropriate? Okay. Okay. So these are the 4 different types of hypersensitivities. Type 1, known as anaphylaxis, type 2, so on and so forth. So you need to know the numbers and you also need to know the names. Heads up, these show up throughout the entire quarter. Okay, these show up throughout the entire quarter. So this is just be an overview, and then we're going to kind of get into it. With a type 1 hypersensitivity or anaphylaxis, this is where basically IgE, that's not me. IgE binds to mast cells. Type 2 is cytotoxic. This is basically where your immune system attacks host tissue. Okay. So type 2 hypersensitivity or cytotoxic reaction is when your immune system attacks you. There's another name you've probably heard of these kinds of diseases. What's another name for these diseases where your immune system attacks you?
Autoimmune.
These are autoimmune disorders. Awesome. Okay. Type 3 is complex mediated. So this is where we have basically improper disposal of, and this is kind of a long word here, an amino complex. So we'll talk about what an amino complex is here in a little bit. Improper disposal of an amino complex. And then finally, type 4 hypersensitivities or a delayed hypersensitivity. This is where your first exposure leads to sensitization. That's probably a Z. And your second exposure leads to that hypersensitivity. Nope. Oh, I have it. Okay. So again, this is just the overview. We're going to go through each one. All right, so here's a table that's actually kind of helpful to know. I'll give you, like back in the day before COVID, when we had paper tests, I used to have this table with most of the table blanked out and ask the students to fill it in. So hint, hint, nudge, nudge. Probably can expect a few questions from this table. However, you do not need to know this entire table. Okay, I'm going to highlight the parts that you need to know. You need to know the name, whether it be type 1 hypersensitivity. HS stands for hypersensitivity. So type 1 hypersensitivity or anaphylactic hypersensitivity, so on and so forth. You need to know the antibody that is involved. You need to know the response time from initial exposure. You need to know the histology, i.e. what cells are involved. And then finally, you need to be able to provide me at least one example of each. We're going to run through this table. Don't worry. I'm going to try and make things make sense. But yeah, so that's what you're going to be expecting. Think about it from kind of like my perspective. If I'm writing your guys' exams, best case scenario, I have a fill in the blank. What cells are involved in a type 3 hypersensitivity? Okay. Worst case scenario, I turn it into an essay and I ask you, I need you to explain a type 1 hypersensitivity, including the antibody response time histology and an example. Okay. So what I would recommend is create a blank table, which don't worry, I got you, and kind of go through it. With that being said, we do need to edit this table a little bit. This box right here, the rare to no leukocyte involvement, type 3 histology, put an X through it. Okay. Instead, I want you to write leukocytes, or sorry, let's just put in phagocytes. Instead. And honestly, I don't like the examples for a type 2 hypersensitivity. I'll provide you better ones here. Okay. So yeah. This is just the overview. We're going to get into it now. So a type 1 hypersensitivity, what was the other name for a type 1 hypersensitivity?
Anaphylaxis.
Anaphylaxis. Okay. So what kind of happens is with IgE. So anybody remember, what does IgE, what is that involved in?
Allergies and parasites.
Allergies and parasites. What ends up happening is that IgE binds to your mast cells. Now, take for example, if I'm allergic to peanuts, okay? If I'm allergic to peanuts and I eat a peanut, IgE, your antibodies, they're supposed to stick to foreign things. They're supposed to stick to bad foreign invaders, right? Here, I stick to my mast cells. Here, I stick to my own tissue. What's the problem with that? So I want you to imagine something covered in antibodies. What does that look like to your body? If something's covered in antibodies, what do we do to that?
We try and get rid of it.
We try and get rid of it. We try to attack it. Who's going to show up first to take a bite at a crime?
Neutrophils.
Your neutrophils. So IgE here binds to my mast cells. My neutrophils, they don't have eyeballs. They don't know that it's our own tissue. So who's the mast cell going to take or the neutrophil is going to take a bite out of a mast cell. So I'm going to say just keeping it wide here. Phagocyte attacks mast cells. Okay, so why is that a bad idea?
Because the mast cells contain histamines.
Yes. And what happens if you take a bite out of a water balloon?
It's gonna pop.
Yeah, it's going to pop and we're going to release all of that histamine. Or degranulate, sorry. Going to degranulate histamine. Now the problem is IgE is sticking to multiple mast cells. So if I'm a mast cell, neutrophil takes a bite out of me, I dump my histamine. The mast cell next to me thinks we're under attack. So what do you think that's going to do? Dump more histamine, and we're going to keep going down the line. So this is going to lead to systemic histamine release. Okay, I eat a peanut and my whole body starts releasing histamine. Would you consider that excessive / inappropriate? Okay. So IgE binds to those mast cells. We end up dumping histamine everywhere. What's so bad about histamine? What does histamine cause in the body?
Inflammation.
Triggers inflammation, absolutely. What else?
Vasodilation.
Inflammation causes vasodilation. What else?
Capillary permeability.
Increased capillary permeability. Okay, kind of keep that in mind because we're going to tie those in a little bit later here. Okay. So here are some manifestations, some symptoms, however you want to call it. Itching, okay. Urticaria. Anyone familiar with the term urticaria? What does that mean?
Hives.
Yeah, urticaria is going to be like hives. So maybe this is some sort of reaction on the skin. Conjunctivitis. You guys have talked about the conjunctivae or conjunctiva in health assessment yet? That ring a bell? Okay. It's going to be red eyes. Not pink eye. That's a little different. Right? That's what you do to your spouse when your guys are fighting. No? Never mind. Rhinitis. What is rhinitis?
Is it when your nose gets inflamed?
Exactly. Rhinoplasty, rhino is nose. Rhinitis is just runny nose. Hypotension. First off, let's just define that. Hypo meaning low. So our blood pressure is dropping. Okay, that's weird. I eat a peanut. I'm releasing histamine everywhere. My throat's closing up. I can't breathe. That sounds stressful. My blood pressure should go up. But why is my blood pressure going down?
Because of the vasodilation and the leakage.
So this is how I use this term here. Hypotension, secondary to systemic vasodilation. All of my blood vessels are getting bigger, causing my blood pressure to drop. Okay, you guys kind of see how secondary is used? Hypotension due to systemic vasodilation. Bronchospasm. Why is my throat closing up? So if we take a look at your little bronchioles, which we'll talk about in respiratory, this is a top-down view of the airway leading to your alveolar sac. Okay. Now your airway is surrounded by capillaries and blood vessels. Now, we just talked about with a type 1 hypersensitivity or anaphylaxis, I release histamine everywhere. What happens to my blood vessels during a type 1 hypersensitivity?
They dilate.
They dilate. And increased capillary permeability means even more fluids leaking out. So what happens to my airway? That's what we call a bronchospasm. Closing of airway, secondary to what?
Vasodilation.
Mhm. Dysrhythmias, abnormal rhythms. So this is an abnormal heart rate. Abnormal heart rate. Why is my heart freaking out?
It's not getting enough blood.
Part of it might be it's not getting enough blood. So if I have systemic vasodilation, that's going to tank my blood pressure. My blood pressure goes down. My throat is closing up. This is a high stress event. It's trying to compensate between trying to maintain blood pressure and increasing it. So I'm just going to say it's secondary to that systemic vasodilation again. Okay. GI cramps and malabsorption, that's more if you eat or have a food allergy that you've eaten. So I'm not really focusing on that one there. Okay. All right, so here's a nice little picture kind of showing you guys what's going on. Okay, I eat said peanut. Cool. That causes IgE. Now IgE is supposed to stick to the peanut. Instead, it sticks to my mast cells. And then my mast cells will end up dumping a bunch of histamine. Okay. Now, what kind of sucks about a type 1 hypersensitivity is that, remember how I told you like the phagocyte takes a bite out of the mast cell, destroys the water balloon? We need to fix that water balloon. However, when we fix it, we replace it with 2 mast cells or more. So we replace it with more mast cells. So what does that mean about, so let me give you an example. I eat a peanut, I go into anaphylaxis, my throat closes up, the whole thing. I go into the ER, I come out, I'm fine, things are dandy. My body's making more mast cells. So what happens to the second time I eat a peanut? Is my reaction worse, better, or same?
Much worse.
Much worse. So subsequent events, we're talking about like anaphylactic events, become worse due to additional mast cells. So if I go into anaphylaxis by peanuts, would you recommend to me to try to eat more peanuts? No. Okay. So that is a type 1 hypersensitivity. Okay. Now we're talking about type 2 hypersensitivities or cytotoxic. Be careful here. These are not your cytotoxic T cells. These are not involving your CD8 cells. Okay. Type 2 hypersensitivities, i.e. cytotoxic, these are talking about autoimmune disorders. This is when a specific cell or tissue is the target of an immune response. The antibodies involved is IgG or IgM. Okay, analogy-wise, I kind of think of this as friendly fire. My immune system is supposed to target foreign invaders, supposed to target foreign things, yes? But if I accidentally target myself, my immune system doesn't have eyeballs. So if I target myself, I'm going to attack and damage myself. So cellular damage by activated phagocytes. So what kind of autoimmune disorders or what kind of disorders come to mind when we're talking about autoimmune disorders? What kind of examples can you guys think of?
Multiple sclerosis.
Yeah, that's awesome. What else? What other kind of diseases?
Lupus.
Nice.
Diabetes.
Anybody ever watch House? It's never lupus. Type 1 diabetes. Another one, I don't know if people have heard of it, Graves' disease. Hashimoto's. I guess disease. So really kind of like any autoimmune disorders would work here if I asked for an example. Just got to be, again, targeting yourself and attacking yourself. All right, type 3 hypersensitivities or an immunocomplex mediated hypersensitivity. So first off, what the hell is an immunocomplex? An immunocomplex is going to be an antibody or an immunoglobulin that is that has binded, yeah, to an antigen. Okay, so an immunocomplex is an antibody that has binded to an antigen. So I'm going to stop sharing my screen really quick so you guys can kind of see a little bit closer. Stop sharing. Nope. Lord. Okay. You guys see this highlighter, right? So the orange part of this highlighter is a virus, for example. That orange felt tip, that's the antigen. That's the unique fingerprint to this virus and this virus alone. Now, when we make an antibody, that antibody has to be specific to this antigen. The cap here, this is your antibody. You have to learn how to make this. This orange cap, this orange antibody needs to bind to this orange antigen. When they bind, that forms an immunocomplex. With me so far? What should happen? What should happen to this virus now that I've tagged it and binded an antibody to it?
It should get destroyed.
Yeah, a phagocyte should come by and eat it. Right? That's what should happen. Now, in a type 3 hypersensitivity, and I probably go back to the slides here, and we form an immunocomplex. So again, here's your virus, here's your bacteria. We tag it with an antibody. The problem is this immunocomplex gets stuck in a vessel wall. Okay, so imagine like this is your blood vessel. Like my fingers are your blood vessel. How would you get this marker out? How would you get this complex out without assuming that you can't break my grip? How would you get this marker out? Be creative.
They attack the cells around it.
Yeah, you go through and you cut my fingers off. You have to cut my fingers off, or you have to destroy the tissue around this complex. If I'm attacking myself, that's the problem. That's the common theme here with a hypersensitivity. Okay. So going back to it, a type 3 hypersensitivity is when an antigen antibody complex, right? So we have that antibody bind to that antigen, and it is deposited in the vessel walls or extravascular tissue. Okay, so this complex, you had your virus, this antibody comes by, tags it, and now it's stuck in the wall. You need to get rid of it. You need to get rid of it. So how do we get rid of this complex? Well, you need to destroy the wall. Neutrophils come by and attack the tissues. When we finally destroyed enough of our tissue, that complex is free, and now we can get it. Does that kind of help you guys visualize what's going on here? I got another slide coming up with the picture, but hopefully that kind of helps you. So take, for example, serum sickness. Serum sickness, this is often due to or secondary to IV drug use. Often secondary to IV drug use. So today's Tuesday. Well, this is any day, just as good as any other day to start heroin. Okay, so let's say I start doing a little heroin Tuesday at 9 a.m. I'm on a budget. Okay, I'm a teacher. I only make teacher salary. Am I using new needles each time? Probably not. So here's my heroin. I'm going to inject it right into my vein. I'm going to do this over and over again. Now, this needle is dirty. There's bacteria on there. There's pathogens on there. Each time I place it into the vessel, I am cramming these pathogens into the wall. How does my body get those pathogens free?
It has to attack the tissue around it.
Yeah, it has to attack the tissue around the pathogen. It has to attack my blood vessels. Now, what's the problem when a neutrophil takes a bite out of something?
It explodes and dies.
It explodes and dies. So this neutrophil is taking a bite out of my blood vessel. It explodes, it dies. What do I have circulating in my blood now?
Purulent exudate.
Yeah, that's your serum sickness right there. Basically circulating. I ran out of room, so I'm just gonna say pause here. Okay, that's serum sickness right there. Is that hopefully making sense there where it's getting deposited in the wall? Okay. Raynaud's, is anybody familiar with what Raynaud's is? So in your hands, you have blood vessels, right? Raynaud's is when your blood vessels constrict very tight, whether it be cold or emotional distress, but basically your hands turn sheet white. You guys have hopefully seen that before. Now, if I do this, so here's your blood vessel, right? It's not right now really open. If I have Raynaud's, it closes very, very tightly, shutting off blood flow. If I'm dealing with the cold or some sort of infection, okay, here's your pathogen, here's your antibody. Right now, it is inside of the blood vessel. Inside of the blood vessel. When I vasoconstrict, I am physically pushing the complex into the wall. So when I vasodilate out again, guess what? It's in the wall. Okay, I'm not a magician, sorry. So let me kind of put this into words here. With Raynaud's phenomena, this is when vasoconstriction pushes the complex into the vessel wall. Same problem with serum sickness. Now we got stuff embedded in the wall. We need to destroy the wall to get it out. Arthros reactions, I'm just going to say like, not going to go there, just because it can lead to a whole bunch of other things and it makes it a lot more gray. Now, an antigen and an antibody, right? Want to reiterate, this can be any antibody. Technically, any antibody can get stuck. Okay. So just reiterating, all right, here is your pathogen. Notice I have already tagged it. It gets stuck in the wall. So walking you through it, antibody binds to antigen of said pathogen. The immunocomplex is somehow stuck, pressed, injected, whatever. The immunocomplex is embedded / deposited into the vessel wall. Then your neutrophils / I'm going to say phagocytes eat the vessel wall to free that immunocomplex for destruction. Okay, so here I'm just writing it out step by step there instead of like hand waving. Hopefully that kind of helps. So an antibody binds to an antigen. That's an immunocomplex. Should get eaten by a phagocyte. Problem is it doesn't. It gets stuck in a blood vessel wall. Now we have to eat the wall around it so we can free that complex for destruction. Okay. Again, the common theme here is my immune system is causing damage to myself. All right. Type 4 hypersensitivities or delayed hypersensitivities. I'm going to be honest with you guys. This is the one we know least about. It's a little hand wavy because we don't really quite know how it works. Let me kind of explain. Your first exposure leads to sensitization, which means when you're exposed to this one thing, you become sensitive to it. Now, when you're exposed to it again, that's what creates your hypersensitivity. That's what causes your immune system to freak out and hurt you. This is going to be due to your cytotoxic T cells, your cytotoxic lymphocytes. So I'll provide you some examples and then you'll kind of see what I mean by this being hand wavy. Yeah, you have some examples over here, but I like these ones better. For example, a latex allergy. So, do you still find latex in the hospital? Not as much as it used to be, right? Most gloves are nitrile nowadays. Why? Well, you could develop a latex allergy. So let's just assume you guys, brand new nurses, you put on a latex glove. What's going to happen? The first time you put on a latex glove. You'll probably be fine, right? What about the second time? Probably be fine. What about the 100th time, 1000th time? You'll probably be fine. But at a certain point, there's a switch that flips, and all of a sudden you are not fine. Okay. Take, for example, I worked with an exercise physiologist. She collected respirations using latex weather balloons. 30 years she did this, no problem. Her 31st year, problem. Okay. So what I'm getting at is, even though I say first and second exposure, it doesn't have to be 1 and 2. It could be the 1000th and then the 1000th and first time. It could be the millionth time. Okay, this is where that hand wavy part happens. This switch just gets flipped and your body's like, no more, none of this, not ever again. Another example here, poison ivy. Poison ivy actually kind of works more like a first and second exposure. So take, for example, do you know the first time you've ever touched poison ivy? Not really. The first time you've touched poison ivy, your body becomes sensitized. Your body's like, I don't like this. Let's not ever do that again. Do you know the second time you touch poison ivy? Oh yes, that's when the hives break out. You guys get what I'm kind of saying with the delayed hypersensitivity here? Okay, another example here, celiacs. Okay, in a nutshell, can anybody describe to me celiac disease?
You're gluten intolerant.
Yeah, gluten intolerant. And so when somebody who has celiac disease eats gluten, that triggers their cytotoxic T cells to attack their small intestines. Anybody know what age-ish celiac disease usually manifests?
Late teens, early 20s.
Late teens, early 20s. I kind of think of like college age, somewhere around there. So let's assume 18. Child can eat gluten, no problem. They're eating gluten during childhood, ages 1 through 17. They're fine. Then they go to college. In college, that switch flips, and all of a sudden their body's like, no more gluten. You guys see how I'm talking about first exposure or 100th exposure or millionth exposure? At a certain point, when that switch gets flipped, there's no going back. Okay. So those are the examples of the delayed hypersensitivity. Hopefully that kind of helps. So here is overview here, some reading if you prefer. If you don't like my explanations, you got it. All right, so let's kind of recap here just to make sure we're all on the same page. Okay. So name, and we're going to say type 1 hypersensitivity, type 2 hypersensitivity, type 3 hypersensitivity, and type 4 hypersensitivity. Okay, what was another name for type 1 hypersensitivity?
Anaphylaxis.
Perfect. Type 2?
Autoimmune.
We kind of abbreviate to autoimmune, but I'm going to say cytotoxic just for formality. Type 3, that was the immunocomplex. And type 4, what was the name there?
Delayed.
Delayed. Nice. Okay. Next up, the antibodies. So what do you guys remember? What antibody was responsible for anaphylaxis?
IgE.
IgE. Type 2, which antibodies are targeting and therefore causing me to attack myself?
IgG.
IgG and IgM. Those are usually tied together. Type 3, what antibody can get stuck in your blood vessel?
Any type.
Any of them, exactly. Type 4, there's none. Because again, it's your CD8 cells that are misbehaving, not your antibodies. Okay. All right, so response time. So I'm allergic to peanuts. I eat a peanut. How soon will I have an anaphylactic reaction?
Pretty soon.
Yeah, it's pretty immediate. Mhm. Very good. Okay. Autoimmune disorders or cytotoxic hypersensitivities. Depends on which one it is, but usually it takes a few days to completely destroy the organ or that tissue. Okay. To find a random immunocomplex in your blood vessel, that can take months. Okay, now let's use latex allergies again. How long does it take typically for a person to develop a latex allergy?
Years.
Years. If you notice, it kind of goes in chronological order. It's kind of nice. Next up, let's talk about the histology or the cells involved, the cells that are causing the issue. So type 1, the cell that's causing the issues, those are your mast cells. Okay. Type 2, who's attacking my own tissues? Who's attacking my own organs?
Phagocytes.
Phagocytes. You can put neutrophils if you wanted to. I'm just leaving it kind of general. Just kind of weave it in. Okay. And phagocytes are the ones eating my blood vessels. Okay. Your type 4 hypersensitivity, this is your T cytotoxic or your CD8 cells. Finally, examples. So I'm going to just tell you right now, the example for a type 1 hypersensitivity, the example for anaphylaxis is anaphylaxis. Good enough for me. Okay. Type 2 hypersensitivities. I think you guys had lupus, diabetes, type 1. Hashimoto's. Somebody mentioned multiple sclerosis, that would be fine. Okay. Graves' disease is fine. Immunocomplex, your two examples were serum sickness and Raynaud's. And then your delayed hypersensitivities, latex, allergy, poison ivy, celiac. Okay. All right, so with these 4 different hypersensitivities, hopefully this kind of helped you guys see the difference between them. As a heads up, people are weird. You guys don't need me to tell you this, but people are weird, right? So let's just assume I have lupus. All right, I start attacking my own cells. If I tag one of my cells with my antibody and it gets stuck in a blood vessel, my type 2 hypersensitivity also now becomes what other kind of hypersensitivity?
Type 3.
Type 3. You guys see what I'm talking about? Is like there is interplay. You can shift between the different categories here. So just kind of be flexible with that. These do keep showing up all over the bloody place. Okay. Okay. So just kind of some definitions here, nothing too crazy. Allergy, harmful effects in your response to environmental antigens. Sunflower isn't going to kill you. Your body doesn't know that. Okay. Autoimmunity, auto meaning self. So this is when you have lost tolerance. You can no longer tolerate yourself, so you attack yourself. Alloimmunity, there's actually a slide coming up, but it's basically tissues of another individual. Type 1 allergies, or sorry, allergies usually associated with type 1 hypersensitivities. They are by far the most common hypersensitivity. Don't need to worry about that second point. What can a person be allergic to? Anything, right? So don't need to worry about that second point there. Autoimmunity, and we mentioned this is the loss of tolerance. A little bit of recap here. What immune cell, what adaptive immune cell controls tolerance?
T regulatory.
T regulatory, nice, exactly. So it could be a problem with our T regulatory cells. Could be, it could be other sources too, but just recapping. Issue is we have identified ourself as the foreign invader. I'm just gonna say an X through this second one here. We'll talk more about glomerulonephritis in exam 5, but for now, just worry, autoimmunity, it's when you attack yourself because you've lost tolerance. Okay, so here's kind of an example of an autoimmune disorder. Systemic lupus erythematosus. First off, let me tell you, you will never need to spell this. Okay, if you did have to spell it, you are welcome to abbreviate SLE. So let me kind of explain to you guys on your exams, on the free response, you can use abbreviations. I'm cool with that. But you can only use abbreviations that we have standardized in class. Okay, so take for example, if I asked you guys right now, what does ROM mean? ROM. You guys haven't heard of that?
Range of motion, that's all.
Range of motion, that's typically what it means, right? Not an OB. ROM means rupture of membrane, i.e. it's go time. So what I'm saying is you can use abbreviations, but just use the ones that we standardize in class. I'm a bit of a boomer, not gonna lie. Somebody wrote LOL, like LOL, on their free response ones. It took me 10 minutes to figure out that they were joking. Okay, so just like, hey, let's use common abbreviations. So SLE, or systemic lupus erythematosus. What's the issue here? Basically, we make antibodies against nucleic acids We make antibodies against our own DNA. Erythrocytes, what are those?
Red blood cells.
Red blood cells, nailed it. Coagulation proteins, I'm just going to leave it as that. Phospholipids, these are our cell membranes. Lymphocytes, what are the two types of lymphocytes?
T cells and B cells.
Mhm. B and T cells and platelets. Okay, so big picture here. You're making antibodies against your DNA, your red blood cells, coagulation factors, your cells, membranes, B and T cells, your platelets. Problem? Why is this such a big problem?
It's literally attacking like your whole body.
It's attacking everything. Yeah. Attacking basically everything in the blood. Do you need blood? So if you attack everything in your blood, so what kind of hypersensitivity is SLE?
Is it type 3?
Almost. This is where I'm attacking my own tissues or my own cells.
So 2.
Type 2. But remember, we're attacking things in my blood. So what happens if a red blood cell gets lodged in a blood vessel later on?
It can turn into a type 3.
Exactly. So it started as a type 2 and then it became a type 3. Here's your critical thinking now. You're a nurse. Your patient has SLE. What is the treatment you would expect? How would we help this person? Whenever I ask these kinds of questions, you need to look at what's the problem.
Would they receive blood from like a healthy person?
Great. So let's say I have lupus. You give me new blood. Okay. Would you be up for giving me new blood every week? And unfortunately, those antibodies are going to attack that new blood too. Can't do that.
What about dialysis, maybe?
Maybe dialysis, that'd be great. Does anybody know how much dialysis costs?
A lot.
Yeah, teacher salary. Greg, you bring up immunosuppression. So in SLE, what's the problem? My immune system is overreacting, attacking me. So maybe I can turn down my immune system. Maybe we can suppress it. Okay, so we haven't gone there yet, just foreshadowing for pharm. Steroids. Steroids are immunosuppressive. Steroids is going to be cheaper than dialysis and probably a little bit more cost effective than blood donation or blood transplant. Okay. So whenever I'm asking about like a treatment or something like that, always go back to what is the problem? What is causing the problem? In this case here, the blood is fine. The blood's just sitting there. It's the immune system that's overreacting. Okay. Does that hopefully kind of make sense? The nice thing about SLE, it sounds absolutely terrible, but it's actually not that bad because it comes in waves. It'll kick on for about a day or two and then kick off for a few months, but it's going to be a really shitty 1 to 2 days. All right, alloimmunity. This is just basically when your immune system reacts to tissue of genetically similar, dissimilar members of the same species, i.e., organ rejection. Okay. Let's say, I don't know, Nicole, you're feeling generous and you give me a kidney. Why does my immune system attack my new kidney?
Because it doesn't recognize it as self.
Exactly. It's not my own kidney. So what do you guys think treatment would be for my new kidney? How do I prevent myself from rejecting my kidney?
You're on like immunosuppression drugs for like the rest of your life.
Yep. And that's commonly what we see with organ transplants or tissue transplants. Okay, so blood typing, it's important, not going to test you on it. RH incompatibility, you don't need to write this down, but if this is your area, this is what you're interested in, this is actually kind of cool. So RH, this is your rhesus factor. This is what makes you positive or makes you negative. Okay. Now, what could happen is if the mother is negative, but I'm going to say first born is positive. If the mother is negative and her firstborn is positive, so A negative versus A positive or whatever, what's going to happen? What's going to happen to that developing fetus?
The mother's cells are going to attack the infant.
Actually, it's kind of weird. You are close, but the reason why I kind of asked it is this works like a delayed hypersensitivity. The first one is completely fine. The issue though is the first time, that's your sensitization. If the second born is positive, this is when we attack the fetus. So first time is that sensitization, second time is that hypersensitivity. What's freaking crazy to me is there's a shot for this. Mothers can receive, it's not exactly a vaccine from my understanding. It's some sort of like medication that prevents the mother from attacking her first or her second or third.
It's called Rogam. I had to get it because I'm negative.
Robium. Thank you.
Yep.
Holy freaking cow, we can do that now? That's freaking awesome. I don't know. So if you're into OB, that's like one of the few things I know. All right. So we talked about flora. This is that competitive market. Opportunistic microorganisms. So bluntly put, these microorganisms are normally not a threat. However, they need an opportunity to cause an infection. Okay, so opportunistic microorganisms, normally not a threat, but they need some sort of opportunity. If they have an opportunity, they're going to cause an infection. Remember how we talked about MRSA? Rotting holes in our skin? Normally not a problem, but if MRSA gets into an open wound, that's the opportunity. Now we have problem. Okay. I'll give you guys another example here in a couple of slides. Okay. All right, let me see. From this slide on, I don't know, slide 26, hopefully that's what you guys have. You can put a line through it all. I think this stuff is fascinating, but this kind of gets into the deep water stuff. Okay, so let me say from slide 26 on, you don't need to worry about it. This stuff will not be on the exam. Okay. And that takes care of the rest of this lecture. So, not so bad. I am going to pause on this one here. So let me kind of give you guys a little bit of a case study. All right, so this actually happened there was a case study for this woman out in California. It was several years ago. Okay, so this patient, female, single mother, I believe she had 2 children. 2 children, single mother, works full time. Lord knows this poor woman ain't got time. Okay, she is busy. So while she's working full time, taking care of her kids, one day she starts feeling the flu coming on. Her nose is a little stuffy, eyes are a little runny, she's feeling a little tired, but hey, work isn't going to do itself and the kids need tending to. Can't stop, won't stop. So she decides to power through it. A couple days later, she's making sandwiches for her kids. She pulls out the bread and smells the bread, and oh God, it is rank. It's bad. It's moldy. It's terrible. Throws it away. She just gives them, a few dollars for hot lunch at school. They go on their way. About a week later, her symptoms don't clear up. She's still congested. In fact, she's even more congested. Now she can't smell anything. Her eyes are still really itchy, and now she's running a bit of a fever. You know what? Week of this, screw it. I'm going to take a day, just feel better, then get back to it. She goes down to take a nap. I'm going to say about 4 or 6 hours later, she wakes up with the worst headache she has ever felt. A little bit of fuzziness in her right eye vision. So she's lost a little vision in her right eye. That's weird. What's going on? She goes to blow her nose. She goes completely blind in her right eye. Okay, now it's time for the emergency room. She goes to the emergency room. They do, I believe, a CAT scan on her head, and they found fungal infection that has taken over her nasal sinuses into her head. It is so infested by this fungus. They have to amputate 70% of this poor woman's face. What happened? Now, if you smell bread, are you at risk for developing a fungal infection? Not really. Why did this poor woman have such a severe fungal infection?
Could the spores from the fungus have gone into her nasal cavity and just kept growing and growing?
They started growing and growing. And what happened before she smelled the mold?
She was already compromised because she was already sick.
She was already immunocompromised. That's what I'm talking about with opportunistic microorganisms. Normally bread, no problem. But because her immune system was weakened fighting the cold, those spores got up there. It's dark, it's warm, and there's plenty of humidity in there. So, moral of the story, don't smell your fucking bread. I don't know. I actually have a very rational fear of mold. Rational fear, and it's because of that case study. Okay. So you guys kind of hopefully get how opportunistic microorganisms work. Normally not a problem until they are. Yeah, that's done. That's done. Don't need to worry about that. Don't need to worry about that. Parasites, I would love to do a whole class on parasites, but alas. Okay, so let's talk a little bit about the exam because I'm pretty sure you guys are a little curious, yes? We'll talk about the exam and then we're going to get into Neurophys. Well, actually, we'll talk about the exam and then we'll have a break and then we'll get into Neurophys. So exam number uno will happen the 18th. Okay. You guys, I see you guys at 8 in the morning. So it will open at, no, I don't see you guys at 8. I see you guys at 8:30. Sorry. Okay. And you will have 75 minutes, so an hour 15. So it goes till 9:45. Okay. So how it kind of works is very similar to your quizzes. One question at a time. No backtracking. One attempt. Okay, so it will happen in class. So please make sure you bring your computers. If you don't have a computer, let me know so I can kind of check one out for you with academic support. Okay, it's just a Chromebook. It's nothing too fancy. It will be through Canvas. You don't need to do ProctorU. You're just gonna, I'll be sitting right there with you so you can ask me questions. That's totally fine. Okay, again, you're looking at 75 minutes. You don't have to use that full time. Okay, I'm gonna pick on poor Greg here. Let's say Greg finishes at 9 o'clock. If Greg, you want to go get brunch, get a few mimosas in before 9, you do it. Doesn't matter as long as your guys are back by 9:45 because that's when I'll start lecturing. Okay. In terms of topics, basically everything from day 1 up till now. So Gen Bio, genetics, cancer, innate, oh my God, innate and adaptive immunity. What we covered today was hypersensitivity, or I guess I should say deficiency / hypersensitivity. Okay, that will be the cutoff for the topics for exam 1. Now, when we come back from break, we're going to get into Neurophys part 1. After the exam, Neurophys part 2. Why? Because Monday, or sorry, the next Wednesday, so a week from now, that's what your quiz is on. Neurophys part 1 and part 2. Okay, so things kind of stack that way. So let me say like quiz, is it 4 now? Will be Neurophys. Ooh. Neurophys 1 and 2. That happens a week from now, so Tuesday. In terms of questions, I'm gonna be honest with you guys. I tried staying up. I couldn't, so I didn't finish it. I'm sorry. So these are rough estimates. You're looking at, I think, roughly about like 30-ish multiple choice questions. I think I maybe have 2 select alls in there. I know you guys hate select alls. I hate them too. I hate writing them, but sorry, NCLEX has them. You're looking at, I think, like 5 short answer. Now, what I mean by short answer on this exam here, it's basically fill in the blank. You should be able to answer these short answers with 1 word. Okay. trying to remember if I like, because I was planning this out in my head. I don't know if there's an essay. I don't know if there's an essay. Yeah, I think it'll be, say like 2 essays. What I mean by essays is not actual long essays. You can honestly finish these essays in 4 bullet points. Okay. Now, what ends up happening is when you take your exam, the computer is going to grade your exam. It's going to grade the multiple choice. Cool. It's going to grade the select all. Awesome. It's going to also grade your short answer and your essays. The problem is maybe you write in, I don't know, if the answer was like autoimmune and you misspell autoimmune, it's going to count it wrong. Remember how I told you guys I don't care about typos? I go through, as you guys are finishing your exam, I go through and I hand grade your essay, your short answers, and your essays. So what I'm trying to say here is when you submit your exam and you're like, I got a 65% on this exam, what the fuck? Don't freak out. Give me a few minutes because I grade them as they come in. I regrade everybody and just double check to make sure things are good. Your grade will go up. Okay. So I'm just saying, like, don't freak out when you finish your exam. You're like, "Grr." Okay. Because in truth, your short answers and your essays can range anywhere between like 10 to 20%. Okay. Again, just give me a few minutes. Let me grade everybody's. You should know your grade. I'm usually pretty good about grading. I don't like to leave anybody hanging. You should know your grade before we start class again for at 9:45. Okay. Now what happens is after the exam that night, I'm going to go home and I'm going to do this crazy stats analysis on the exam where I look at every single question. I see who got it right, who got it wrong. The computer assigns like this weird by serial number. What I'm saying is I go home that Monday and I analyze each question to basically make sure, is it fair or is it not? If it is unfair, because maybe I made a mistake, I'm not perfect. Maybe I forgot to include the right answer. Maybe I miskeyed it. I go through and I do this question analysis, and what happens is I will drop a question. Now, when I drop a question, how that works, it doesn't matter what you put, you will get the credit for that question. Okay, so if the answer was A, but you put B, you'll still get credit for it. The only problem is if you originally put A and you got it right, and I dropped that question, it doesn't really do anything for your score, right? So I generally only drop questions in the best interest of the group, not for individuals. But yeah, so again, your grades still might kind of fluctuate and change a little bit in the evening, but I should have the exam grades finalized by Monday late evening. I don't get home till 8 apparently. So just heads up about that. Questions about the exam, what to expect, etc.
So basically for the essay questions, you don't care if it's formatted pretty, you just want correct
No.
bullet points. Okay.
Bullet points, short, sweet, simple.
Okay.
I would say if you use complete sentences and correct grammar and formatting, you're going to wait until next week for your grade. I don't have time for this. If you want to know your grade, keep it short, keep it simple, easy for me to grade, done. Okay.
Would you be able to like give us an example of what an essay question could possibly look like?
Absolutely. Maybe I ask, what are the defining characteristics of cancer? All right, well, P53, double knockout. Your proto-oncogene is now an oncogene, 6 bullet points there. Or I can ask, maybe I ask you to list them out. List out the adaptive immune cells and a brief description of their functions. Okay, well, T helper cells coordinate the immune system. T cytotoxic kills viral or cancerous infected cells. I can ask, what's another one? Maybe I ask you to explain hypersensitivity. So type 1 involves something like that. I'm not asking for a philosophical paper on whether you feel that lupus is worse than a latex allergy. Yeah, good question. Any other curiosities? Going once. Going twice. All right, let's take a little break. Let's say like a good decent break here. So let's like 10 minutes. So like 9:57, we'll pick back up again. Okay. And if you guys do have questions during your break, just pop them into the chat. I'll be running around. Oh, all right. Cool. So any questions while we were at break? Awesome. So now we get into Neurophys. Okay. So this will be the kind of the start for exam 2 material or your quiz. Let me just be completely upfront here. This will not be on your exam. Okay. So in terms of nervous system stuff, keeping it kind of broad at first, what's the whole purpose of the nervous system? Well, you guys have probably gone over this plenty of times during anatomy, right? Communication. Okay, 3 basic functions of the nervous system. Don't think about it too hard. The answers are on the next slide. Detect, evaluate, respond. Well, what could it mean to detect something? Don't worry, the definitions are on the next slide. All right, so you can feel free to organize this nervous system however you want. This is personally how I organize the nervous system in my head. This kind of makes sense to me. So thinking at the very top here, you got your brain, brain stem, and spinal cord. Now, some people want to combine the brainstem with the brain. That's fine. I kind of keep the brainstem separate, just the way my brain works. But just recapping here, your brain and your spinal cord make up which nervous system?
Central nervous system.
Central nervous system. So we can abbreviate the central nervous system as CNS. Okay. Now, below the central nervous system, okay, there's 2 things that we can do. Either we can talk to the brain, central nervous system, or our central nervous system can talk to us. That's it. Okay. If we are sending signals to the brain, what kind of signals are we sending? What kind of information do you want to send to your brain?
Sensory.
Yeah, sensory information. That's awesome. Another way to say that is you can be sending afferent signals to the brain or ascending signals. 3 different ways to say the same thing. Sensory, afferent, or ascending always goes towards the central nervous system. Therefore, going away from the central nervous system is just the opposite. What's the opposite of sensory?
Motor.
Motor. Afferent will be efferent. And then descending. Okay. Now, of the motor, of the efferent, of the descending signals, there are 2 types. Okay, it can be autonomic or it can be somatic. What's the big difference between the 2?
Autonomic is like self-regulated, like it does it subconsciously. Somatic is conscious movement.
Yep. I'm going to use the term involuntary versus somatic, which is voluntary. Okay, so what is an example of a somatic signal? What's an example of a voluntary movement?
Moving my arm.
Yeah, exactly. Skeletal muscle. Perfect. Now, of your autonomic nervous system, there are 2 branches. Parasympathetic. Oh, Lord. And sympathetic. Does anybody remember the motto of the parasympathetic nervous system?
Isn't that fight or flight?
Other way around. This is the way I personally remember it.
Rest and
Parasympathetic.
digest.
Yep. The way I remember it, parasympathetic starts with a P. You know what else starts with a P? A pillow. Little old school, like little old med school trick for you. Rest and digest. Yes, I had dreams of going to med school at one point. Then I looked at my GPA. Sympathetic, therefore, must be fight, flight, and because I'm a nerd, freeze. Oh, I kind of explained that, but you guys are just responsible for fight or flight. Okay. Now, this rest and digest comes with an asterisk. During parasympathetic activation, when you are resting, what kind of muscles are resting? Smooth, cardiac, or skeletal?
Smooth.
You guys got it. Skeletal muscle is relaxing. Smooth muscle, part of your GI tract, that's the digestion. It has to be very, very active. Okay. So just be careful here. When we say rest and digest, we're talking about skeletal muscle resting. Your smooth muscle is extremely active. So if everything in blue is the central nervous system, what would purple be?
The peripheral nervous system.
The peripheral nervous system. Okay, so just in terms of naming conventions and abbreviations, for me, when I use the term PNS, that's referring to peripheral nervous system. I will never use PNS for the parasympathetic nervous system. Okay, so PNS is always the peripheral. Okay, be careful saying this abbreviation. You do not want to say this abbreviation too quickly, especially in the face of patients. You have no idea what I'm talking about. Just say it out loud while you're muted. Oh yes, it's week 2 and we're already into the penis jokes. All right, so you got the central nervous system, brain, spinal cord, straightforward. Peripheral nervous system, everything else, what we just wrote down, afferent, ascending, sensory, all the same thing. That's going towards the central nervous system. Efferent, descending, motor, all going away. Okay. All right, so talking a little bit about the cells. Here you got your neuron. Simple enough. Couple of structures you need to worry about with the neuron. What I mean by this is you should know what each structure kind of does. You need to know the dendrite. You need to know the axon terminal button or button. You need to know the soma, axon, myelin sheath, and one more thing, this point right here, that's called the axon hillock. Okay, so again, roughly know what those structures do because some of these structures can be affected by disease. So keeping it simple, dendrites, they are the receptor arms of the neuron. The dendrites receive signals. Axons is the delivery arm, i.e. they send or transmit signals. Okay, so you guys are aware your brain is just comprised of a bunch of neurons, right? What are the two states of a neuron?
Excited or unexcited?
Perfect. It's either firing electricity, i.e. excited, or it's resting. Wrap your heads around that. Your brain is filled with millions of these, and it's either on or off, 1 or 0. Everything that you know, everything that you feel, all of your memories, everything that you are is a series of 1s or 0s. That's why we program computers in binary after the human brain. Freaky, yes? The cell body, i.e. the soma, this is going to decide to fire or not fire. Now, what I mean by fire is fire and action potential. The soma decides, do we send a burst of electricity or do we hold? Do we fire an action potential or not? Okay. Talked about dendrites, talked about axons, cool. Axon hillock, the AP, the action potential begins here, i.e. this is where we generate the electricity. That's not how you spell electricity. There we go. This is where we generate the electricity for an action potential. Now, your myelin, this is that insulating layer of lipids, fat. Fat is a great insulator. Okay. It helps speed up conduction. So kind of think it this way. You're looking at a computer right now, yes? And I'm assuming your computer is plugged into the wall. I will pay you $5 to grab your power cable right now. Would you? No, he's shaking her head. Like, yeah, I'm down for making $5. If you grab your power cable right now, you're okay because it's wrapped in that shielding. Same thing with your myelin. Now, what if we take off that shielding? What if we take off the myelin, the lipids? If I take off the shielding around your cable and I pay you $50, would you grab your power cable now? I don't know. Ashley is looking a little like, I could use $50 right now.
I've been shocked by cars multiple times, so I'm not scared.
No, we're not messing with car batteries. So the issue there is if you don't have lipids, if you don't have shielding, that electricity leaks out. That's kind of what happens here with multiple sclerosis and Guillain-Barré. Now, you don't need to worry about these yet. We're going to have a whole lecture on neuropathologies, just kind of foreshadowing. Okay. All right. So there are 3 different types of neurons. Sensory neurons. Sensory neurons, question for you. From which nervous system to which nervous system do they connect? Central versus peripheral.
Peripheral to central.
Yeah, your sensory neurons connect your peripheral nervous system and send information to your brain, your central nervous system. Okay. Motor neurons, other way around. Your central nervous system to your peripheral nervous system. Interneurons, what we're going to talk about, these are located at the central nervous system. Okay. All right, so neuroglia, these are other cells besides your neurons. They kind of do stuff. Oligodendrocytes, these are responsible for making myelin, at the central nervous system. Versus Schwann cells, they make, I don't know why I changed pretenses there. Myelin at the peripheral nervous system. Epididymal cells, these are going to produce CSF. Anybody familiar with what CSF stands for?
Cerebral spinal fluid.
Cerebral spinal fluid. Therefore, cerebral spinal fluid, is that central or peripheral nervous system?
Central.
Perfect. Astrocytes, astro meaning star cells. These are going to weave together to make triple B, your blood-brain barrier. And then finally, your microglia. These are going to be phagocytic. And they're going to basically eat debris and old cells. Now notice your microglia are phagocytic. What other bodily system have we covered thus far contains phagocytes? What other bodily system
The
have we
immune
talked
system.
about? Sorry, say again?
Immune system.
The immune system. If a cell is phagocytic, it means it's actually always immunologic. Whenever a cell is a phagocyte, it's actually an immunologic cell. It's performing some immunological function, i.e. cleaning. Okay. So here are all of your cells playing along. Cool. All right, your blood-brain barrier, i.e. triple B. Okay, your blood-brain barrier, its job is to keep the things in your blood separate from your brain. Why? So it exhibits selectivity, allows only specific things to cross from blood to brain. So these are made of your astrocytes, these little stars weaving together. Would you say your blood-brain barrier is useful? Yeah, I would say so. It's kind of nice to keep those two things separate, right? If you have an infection in the blood, do you want it in the brain? So this is generally pretty helpful. The problem is, you don't need to write this down. The problem is we have no idea how it allows certain things through and other things not. Take, for example, nicotine, drugs. Can you imagine what would happen to drug addiction if we could just stop them from crossing over into the brain? Solve drug addiction like that. the blood-brain barrier, we just don't know enough about it. So medications can change too, between male and female, size, age, etc. Some people, the medication passes into their brain, no problem. Other people, it's a lot slower. So as a nurse, the triple B, the blood-brain barrier, can actually make your job a little bit more difficult. All right. So this is going to be the meat and potatoes here of this lecture. Okay, talking about action potentials now. When we're talking about the nervous system, okay, here is your neuron. And if you're wondering, yes, I do have a bachelor in arts. I actually have a BA and I'm a little salty about it. Thanks to you. All right, so here's your neuron. Inside the neuron, we're going to be sending electrical impulses, i.e. the action potential. So within the neuron, there's this burst of electricity. Here's your action potential. Okay. Notice your neurons, they're not physically touching each other. How does a neuron communicate with another neuron?
There's synapses in between the neurons with receptors for channels.
Yeah. These chemical signals, these are neurotransmitters. Okay. So what I'm getting at is your nervous system is not just electricity, it's alternating. Okay, it's alternating. It goes electricity to chemical, electrical, back to chemical, electrical, finally ending with chemical. Okay. Again, so your nervous system is actually both electrical and chemical. They alternate with one another. What we're going to be talking about is just the electrical part right now. We will talk about neurotransmitters, but just right now we're talking about action potentials. Okay. All right. So here's an example of a neuron, and it is at rest. At rest. Okay. Now, you don't need to remember these specific numbers, just kind of look at the bigger picture here. K plus, this is potassium. Heads up, in the medical field, everything is abbreviated into its elemental form, and I'm lazy, so I'm never writing out potassium. I'm going to write K plus. Okay. So potassium, where is the majority of potassium? Do we have potassium mainly on the inside or outside of the cell?
The inside.
Inside. So the way I abbreviate this, concentration of potassium is primarily inside the cell, inside the neuron. Okay. Now we're going to skip calcium. Why? Because we're going from nothing to nothing. That's just so small. So don't worry about calcium here. Okay, what about Na or sodium? Where do we find the majority of sodium while at rest?
Outside the cell.
Outside. This is our baseline, is at rest. This is where we want to live. This is when we're ready. We're not doing anything. This is where we are. You need to know this. At rest, the potassium is inside of the neuron and the sodium is outside of the neuron. Okay. All right. So just recapping what we just talked about, at rest, inside the cell, we have mainly potassium. Outside of the cell, we mainly have sodium. Okay. Now, when a neuron fires an action potential, that happens in 3 stages. An action potential has 3 parts to it. Part 1, depolarization. Part 2, repolarization. And 3, hyperpolarization. Okay. All right, so here, sorry, my gray line doesn't really show up very well. On your guys' printed notes, do you guys see that dashed line, hopefully? Show up okay? All right. It's just on my screen, it's a little washed out, so I'm gonna draw mine in here. Okay, so continue to this graph here. This solid line, this is the line representing rest. Anybody remember from Neurophys what that dashed line above it means or represents?
Isn't that the threshold?
Threshold. Threshold. Okay. So don't draw this part yet. It's gonna get a little messy. So right now I'm at rest, my neuron's at rest, and then it gets to this point right here. What's gonna happen? Nothing. Why? Because neurons work on the all or nothing principle. We have to get the threshold. Again, don't draw this line yet. So doesn't matter if it takes 3 years for it to get there versus that. Is there going to be a difference? No. As long as we get to threshold, that's all that matters. Okay. All right. So now this is what we're going to start drawing. Okay. So here we meet threshold. Once we meet threshold, the first phase. Actually, let me use traffic colors because that'll make sense. First phase. Maybe that yellow does not show up well. Second phase. Third phase. So what was the first phase of an action potential? What was the first step called?
Depolarization.
Depolarization. Okay. Second phase, repolarization. And what is the final phase of an action potential?
Hyperpolarization.
Hyperpolarization. Okay, so those are the 3 phases, not too bad, right? Again, depolarization begins after we meet threshold. Okay. We good with this, hopefully? Now we're going to make it a little bit more complicated. This is where the nursing kind of ties in now. You need to describe to me the movement of electrolytes throughout the different phases. You need to tell me what channels are open, which channels are closed, where's the majority of potassium, where's the majority of sodium throughout this action potential. Okay, so I'm just redrawing what we just drew. Yeah, that'll work. Okay. So again, this black line down here, that solid black line, that represents rest. So I'm going to say we are at rest. Now, helping you guys work this, when we are at rest, where is the majority of your potassium?
Inside.
Inside. And the majority of your sodium is where?
Outside.
Outside. Okay. Now, let me say, if you can start here if you can remember this point right here, you can rationalize your way through this entire thing. You do not need to memorize, or I say you shouldn't try to memorize all of the little details. It's just not going to happen, okay? Instead, build a logical path between step A and step B. If you can logically trace this out, you don't have to memorize a single thing. All right, so let me show you a case in point. Right here, right where we meet threshold. Okay, right where we meet threshold, that's where the sodium, actually, let me write that up a little higher. That's where your sodium channels open. Now your sodium channels are open. So what is the only electrolyte that can move in or out of the neuron?
Sodium.
Sodium. Now, looking back at your concentrations, we know that sodium is moving. Where? Is it going into the cell or out of, I keep saying cell. Is it going into the neuron or out of the neuron?
Out.
So most of my sodium is outside already.
It's going in. I misspoke.
Yeah. So sodium flows into the neuron. You guys get hopefully what I'm saying here? If your sodium channel's open, only sodium can move. Where does it want to move? It wants to move to the opposite. If it's outside, it wants to come in. So now let's take a look at our apex. Okay. So I'm going to ask you the same question. Where is the majority of my potassium?
Inside.
Inside. Why is it still inside?
Because the potassium ion channel hasn't opened yet.
Exact. Only sodium channels opened. That's it. Potassium didn't move. You see what I'm saying here, guys? Only one ion moves at a time. And if you can logically trace this out, you can already tell what's going on. Therefore, the only thing that should have changed is sodium. Where is the majority of my sodium now?
Inside this neuron.
Inside. Yeah, inside the neuron.
I
Yeah,
almost
sorry.
said cell, damn it.
I don't know why I keep saying cell. I'm sorry, guys. Neuron. So at the top here, your sodium channels close. Your potassium channels will open. So therefore, what electrolyte is moving and where?
Potassium's moving out of the cell.
Out of the cell, out of the neuron, yeah. Potassium flows out of the neuron. Cool beans. So that brings us back to down here. This solid line, when we are at the solid line, what state are we in?
Rest.
We're at rest. This is where your potassium channels close. So taking a look here, we are back at rest. You got potassium and you got sodium. Now, where is the majority of my potassium?
It's on the outside.
It's on the outside. And where's the majority of your sodium?
Inside.
Inside. I agree. Okay, that's it. We're back at rest. I'm joking, Megan. I'm being totally sarcastic. Just heads up. We're back at rest. Job's done. Mission accomplished. why do I have more of this graph left? Why am I not done yet?
Because the neuron still needs to go back. So it like dips below and then it comes back to rest. Like there's still
Wow.
hyperpolarization to go through
Still, but why? Why do we need to hyperpolarize?
to get prepared for another action potential.
Take a look at these two. They're both
You
at
gotta do a
rest.
switcheroo.
Yeah. So this is your why. Why do we need to hyperpolarize? We're already at rest. Why do I need to get back to rest again? Notice everything is opposite. So what I'm getting at here is when we started, this is true. Oh, that's terrible handwriting. When we started, that was true rest. Where we just left off, yeah, we're at rest, but that is not true rest. Okay, this is the why. This is why we need to have sodium potassium pump turn on. And then finally, we got our sodium potassium pump off. Sodium potassium pump, this is the only time where you move two ions at the same time. Just kind of switch it, but now we get K plus is on the inside. Sodium is now on the outside. Would you say that we are back to true rest after hyperpolarization? Why?
Because it returned back to the same concentration it was before.
Yep, exactly. The potassium is back on the inside and sodium is back on the outside. So now, can you say that we're done? Mhm. So question for you guys. Where is the majority? Where is the majority of potassium at the end of depolarization? Okay, so where is the majority of potassium at the end of depolarization?
Inside the neuron.
I agree. Inside the neuron. Where is the majority of potassium at the start of repolarization?
Still inside.
Polarization. Still inside. Okay, what just happened there? Two different questions, same answer. Why? Because they're talking about the same spot. That spot is the end of depolarization, i.e. the start of repolarization. Okay. Now, are you going to try to memorize where each electron is at any given point? Where each electrolyte? Oh God, no. As I had mentioned, if you know your starting point, you can logic your way through this whole thing. Okay, so what I want you to do is I want you to practice with this. Get some blank sheets of paper, get a dry erase board. Oh dear God. A dry erase board is one of the best investments you'll ever make in nursing school. Okay. I would steal the freaking dry erase board off of the classroom if I could. Okay. Get a dry erase board, trace this out, logic your way through it. Because guess what? On the exam, you're allowed a scrap sheet of paper. You can write stuff down. You can draw things out. I don't know about you guys, but I'd rather learn one picture than 72 dots of information. Okay, that's my recommendation. Try to think of images and diagrams more so than individual points. So that there is your action potential. Questions? Okay, my challenge to you, trace it out, try to generate it, not from memory, but be able to logic your way through it. Now, if you didn't like my fancy drawing, it's okay. You only hurt my feelings. Here's this in words. Here's a better drawn action potential, I guess. Okay, so here, this slide can get crazy. All I'm emphasizing here, let me not even say that. Your sodium potassium pump is a form of active transport, which means what?
Has to use energy.
It has to take energy. All right, second mind-blowing fact here. How much energy did it take to depolarize? None. It's passive facilitated transport through your sodium channels. How much energy did it take to repolarize?
A bit.
Zip, none. Exactly. It's still passive facilitated transport. It's only when you hyperpolarize does it take energy. So hyperpolarization is a period of rest, yes. It takes energy to rest. It doesn't take energy to contract, it takes energy to rest. How does that affect your skeletal muscles? Anybody ever think about how weird that is? So think about rigor mortis. Somebody dies within 24 minutes. What happens to their skeletal muscles? Or 24 hours, sorry.
Starts getting super, super rigid. It doesn't
Super,
move.
super rigid because they don't have ATP to hyperpolarize. Okay, that's freaking weird. Yeah, ones and zeros, and we're technically zombies. Okay. All right, myelin sheath. Just covering your axon, nothing too crazy here. So example, multiple sclerosis has phagocytes eating the central nervous system's myelin sheath. What hypersensitivity does that make it?
Hypersensitive 2.
Hypersensitivity type 2. Awesome. Because we are targeting specifically our myelin sheath, that is targeting our own tissue. Is it beneficial for you to eat away your own myelin sheath? No. And if we are attacking ourselves, that's an autoimmune disorder. Okay. So that's what you can kind of expect in terms of questions for hypersensitivities, kind of like that. Gray versus white matter. Gray mainly comprised of the somas. So the cell bodies, i.e. proteins. White matter doesn't show up very well. White matter mainly comprised of myelin. Okay. So question for you guys. Why would myelin sheaths be white?
Because it's made out of lipids.
It's made out of lipids. Anybody cook with Crisco lately? What color is Crisco? Bacon fat. Hmm? White. Oop. So, to give you guys a little bit of a break, I know things are crazy right now. Heads up, quiz 4 is going to have a question on this somewhere. Here's your brain. And here is your spinal cord. Oh yes, you get to look forward to a whole quarter of my terrible drawings. Heads up. So there is your spinal cord versus your brain, okay? With your brain, you got a thin layer here. Let's start with the spinal cord. On the spinal cord, which is the most internal? Is it gray or white matter?
White.
Other way around. It's gray matter that is most internal at the spinal cord. Okay. What about the brain? Where would you find the majority of gray matter in the brain, internally or externally?
I want to say external.
It is external. It flips. It flips. Why? Okay, so let's think about this. If you're sending a message from your brain to your spinal cord out to your periphery, do you want it to take a long period of time or a short period of time?
ASAP.
Yeah, ASAP. So once we get the signal here, your myelin sheath acts as a highway. It's going to shoot right out pretty quickly. Now, why would we want white matter on the internal part of the brain? Now, does one part of the brain do one thing independently? No, your brain is communicating with different parts all the bloody time. It's sending a signal over here, which is sending a signal over there, which is now going over there, which is now bouncing all the way over here. So what I'm saying is the white matter in the brain is internal to allow for multiple area communication. The white matter is external in the spinal cord to allow signals to go to the peripheral nervous system as soon as possible. Okay. So now we're talking about the synapses here. Now we're talking about the neurotransmitters. Again, neurotransmitters is what kind of signal?
Chemical.
Chemical versus action potentials. Action potentials were
Electrical.
electrical. Perfect. Okay, so now we're talking about in between the neurons, we're talking about the chemical signals here. Okay. So taking a look, your synapse is this tiny space between the two neurons. All right, taking a look at this slide right here. Okay. So step 1, the action potential reaches the axon terminal button or button. Okay. Step 2, we have calcium voltage gated channels open. Calcium voltage gated channels open. So we're talking about this step right here. Now, if those channels open, where's calcium going?
Inside the neuron.
Calcium flows in. Cool. Why do we need calcium? You see your neurotransmitters, they're in these little bubbles. They're in these little bubbles. The reason why you need calcium is because in order to get this bubble out, there's a co-transporter. You need calcium to get it out. Kind of think of calcium like the key. All right. Calcium and neurotransmitter are released into the synapse. Okay, cool. And then the neurotransmitter binds with the postsynaptic neuron. Neurotrans binds to, I'm just going to say next neuron. Okay. So, question for you. What electrolyte is needed by a neuron to send a chemical signal? What electrolyte is needed in order to send a chemical signal?
Calcium.
Calcium, because a chemical signal is a neurotransmitter. What if I was to flip this? What electrolyte is needed for an electrical signal? Sorry, there should be electrolytes.
Sodium and potassium
Why?
for the action potential.
For the action potential, absolutely. Okay. So as you guys are going through the exam, I want you to hear my annoying voice in the back of your head when you pick an answer. Why? Why? There should always be a reason. Okay. Sorry, people still taking notes on that? We okay? All right, so synapses, your neurotransmitters. There are over 30 different neurotransmitters. You don't need to write this down. There have been over 30 different neurotransmitters thus far. They either do one or two things. Either excite the next neuron saying like, hey, go, or tell the next neuron like, hey, stop. 30 different ways to say yes or no. 1 or 0. Think anybody freaking out that we are a bunch of 1s and 0s? Like this is evidence for the matrix. You understand this, yes?
I was just about to say I might watch The Matrix tonight.
You could be the one. And that is the end of Neurophys, part 1. Okay. So just recapping, exam Monday. I'll be around. If you guys have questions, shoot me emails. I should also have some more free time as well near the end of the week. So if you want to meet for office hours, I'd be more than happy to. Just send me a list of days and times and we'll sort something out. With that, So good luck studying, guys. I also know you got health assessment going. We're spooling up here. I think after exam 1 for patho, following week you'll have exam 2, or your first exam for health assessment, right? Probably, maybe. I'm just going to give you a heads up. Usually it alternates patho, health assessment, patho, health assessment. That's kind of like the tempo for this quarter here. Okay. So good luck. Let me know if you have questions. I'll try to help out. And yeah, I'll see you guys next week. Yeah. Everybody stay safe. Have fun out there.